So today I'm going to try to break down a very important fundamental concept in machine learning and information theory. It's called the callback-Leibler divergence, or the KL divergence. And if you've ever worked in reinforcement learning or GANs or variational autoencoder, you're going to encounter the KL. It's really a core part of what it takes to measure how close two probability distributions really is. So for example, here you have the green and the blue one. So let's dive in and understand what it is and why is it useful. And we're going to also explain the individual components of this formula to understand what KL is really about. So KL divergence measures a kind of a distance between two probability distributions, say P and Q. And these distributions can represent anything you want. So they can be the chance of rain tomorrow, it can be what a real image looks like, anything involving probabilities. And what's difficult with comparing two probability distribution is that they could be different in many ways, not just one way, and that is why you cannot boil everything down to one number. But KL does boil things to one number, and it's because when it compares two probability distributions, it compares it from a certain perspective, which is from a reference model or from a probability distribution that we actually care about. So not all changes are important, is basically what's going on. In KL, some changes are really important, and the difference between the regions where it is important is going to be included when we calculate the KL. I'll touch more about this a bit later. So there's different ways to understand KL divergence. So for example, from the information theory perspective, in information theory, suppose that tomorrow is a sunny day. Okay, so I'm expecting tomorrow to be very likely to be sunny. And imagine that I'm already at tomorrow's date. If it's actually sunny, there's very few information. I'm just going to get, let's just say for simplicity's sake, I'm going to get a 1-bit information that it is sunny because I'm expected it to be sunny. So I don't need a lot of information of that. This is my expectation. So there's very few amount of information that I need to confirm that. Let's say by like a notification on my phone or something like that. However, if it turns out to be rainy, then I'm going to need not just a notification, but I'm going to need, let's just say, an email alert. I'm going to need the news or something like that. So this is like way more bits. And this might not be super well explained, but the idea here is that when I'm not expecting something to happen, there's more bits that are needed to encode that information. And so KL divergence is kind of the amount of the extra information required to predict the weather tomorrow using the samples that I've withdrawn from this model right here. So the more these two distributions are not close together, the more bits it's going to take to actually encode that information, and hence you're going to have a larger KL. Another way to explain the KL divergence is by the surprise factor. So let's just say you have a model here that tries to model what happens in the reality. Since Q doesn't perfectly match with P, there's going to be some surprises on average. And so KL quantifies these surprises, but not just any surprises. It's only the ones that actually matter. And what matters is dictated by this guy. This is what I care about. So let me just go through the components right here. There's about 3 components. There's also the sum here. So we're going to break it down. So whenever you divide a probability distribution or another, this is called the likelihood ratio. Just this by itself is a likelihood ratio, and it tells us that whenever I sample X from this probability distribution, is it more likely to belong to this probability distribution or this one? If it's more likely to belong to P, then this ratio is going to be bigger than 1. If it's more likely to belong to Q, then this ratio is going to be less than 1. So here's an example. Suppose an event is actually quite likely to happen in reality, but unlikely to happen in the model. So when it happens, you're very surprised because you weren't expecting it. Because it happened in reality, so you weren't expecting it, so I'm very surprised. Conversely, if you think an event is very probable in Q, but it's actually rare, it didn't happen in reality, you're not very surprised. And so there is this factor right here that tells us what do we really care about. And what it says is basically we care about what happens in reality. So whenever there's a difference, something that the Q says that doesn't happen in reality, I'm really going to care about it because that's what I specified right here. This makes the error outputted by this guy be weighed much more than the other error, which is when this guy thinks it's really probable, but it didn't happen in reality. That's a big change, but since I don't really care about it, I'm not going to weigh it as much. So it's not going to factor into my KL. And here is a visualization to explain this better. Okay, so you have two probability distributions, the PX in blue and the QX in green. Here, the QX matches very good only a part of the PX, but it's going to have a high KL. Why? Is because we completely missed out this part, and we really care about this part because of this part of the equation right here. So I'm gonna put a really high penalty on this. And this example, the Q doesn't really match very well. However, it covers a lot of what PX covers. So this is going to have a low KL, which is a good thing. So the penalty is going to be really low. And so this is what it means to calculate the difference between two probability distributions, however, focusing on what really matters to us. One last thing I'm going to mention here is this log component. Having the log of the likelihood ratio it's called the estimator. And the log is used here for many reasons. One of the reasons is that it connects to the information theory concept. Probabilities that are multiplied together, instead of being multiplied and leading to very, very small numbers, by using the log, we can add them instead of multiplying them. So it's going to make the analysis easier. The other thing is that it prevents large probability values from skewing the mean information content. So you're not going to have like a single large probability just skew the whole thing. And you also have the sum here is because you're taking many samples, you're averaging out over as many samples as you need to calculate an effective KL. So to summarize, the KL divergence, it quantifies how much one distribution differs from another, and it helps us model situations by minimizing surprises because we care about what happens in reality. So whenever we're surprised in reality, we want to penalize that. And when we include the KL in some kind of a loss function, the bigger the penalty, that means the gradients are going to flow in such a way that the next time I run this, the penalty is going to be smaller. So whether you're coding samples or training a model or analyzing distribution, KL is a powerful tool for guiding all of those. Thanks for watching and hope this helps.